Spline module. 5 spline method can be used to generate the spline matrix G sub K, Kg. Because of the structure deformation is solved by the structure solver at the structure grid, then we need to transfer this displacement from the structure grid to the aerodynamic grid. And after we have the AIC, then we have the structure mode shapes splined on the aerodynamic model. Then AIC times this mode shape will give us unsteady aerodynamic forces. And we have 5 spline methods in the spline module that jointly generate the spline matrix. The first method is called infinite plane spline method, IPS, and the car is called spline 1. And the second method is called thin plane spline method, we call TPS, and the car is called spline 3. The third method is a beam spline method, the car is called spline 2. And the fourth one is called rigid body attachment, the car is called attach. And we have zero displacement method called spline 0. And when we're going to use this spline 0 car, if you use the CL7 to model the wind tunnel wall, and the wind tunnel wall is not a part of the structure model, and so you can put a spline 0 and to make a 0 displacement on those CL7 to model the wind tunnel wall. And the spline matrix transfer the displacement computed at the structure G-set degree of freedom to the aerodynamic K-set degree of freedom. So once you have a spline matrix, it times the displacement at the G-set, and you will transfer this displacement to the aerodynamic K-set degree of freedom. And also, based on the principle of virtual work, one can prove that if you use the transpose of the spline matrix, and you can transfer the aerodynamic forces computed at the aerodynamic K-set to the structure G-set. And then if you sum all the forces at the aerodynamic model to get the total lift or side force, and then after you transfer the force to the G-set, you also can add all the forces to give you a total lift and side force, and those lift and side force is guaranteed to be the same. So this is based on the principle of virtual work. And general guidelines, all aerodynamic grids should be within the domain of a structural grid to avoid extrapolation. And so this is all the bulk data cars in the spline module. Spline 1 is for infinite plane spline. Spline 2 is for beam spline. Spline 3 is for thin plane spline. This is a 3D spline. Attach, you would attach the aerodynamic model to a single structure grid point, and the spline 0 is a 0 displacement condition. And in general, all the spline car, they refer to a set K car, and refer to the panelist 1, panelist 2, panelist 3. In those cars, you list out the aerodynamic panel IDs, and so you want to spline the mode shape to those aerodynamic panels. Then you refer to another set 1 car, and in this set 1 car, you list out all the structure grid point, and so you want to transfer the mode shape from this structure grid to those aerodynamic panels. And we also have a car called plot mode car, and this car can generate a graphic file. Then you can use commercial graphic software to display the spline mode on the aerodynamic model. And then we have a spline M car. You can save the spline matrix or retrieve the spline matrix, because for large model to generate the spline matrix could be time consuming. And we have another car called Spline F. Spline F is that you use the car in case you want to use different strategy to generate different spline matrix for force transferal. And this car spline d.o.f is you want to create additional degrees of freedom in the structural model for spline. The infinite place spline method is derived from an analytical solution of an infinite plane. And so if you have some structural grid point and you have a structural deformation at those grid points, the infinite place spline method will fit an infinite plane into this deformed structural grid, and then once you have the analytical solution of this deformed infinite plane, then you can compute the deformation at any point on the plane. So in this case, you just plug in the aerodynamic grid, and you can get the deformation at aerodynamic grid points. And the infinite place spline method requires a definition of spline plane. So you have to define a spline plane. Then the infinite place spline method will project the structural grid point on the spline plane and to create an infinite plane. Because we need to define a spline plane, and the IPS method requires at least 3 non-collinear structural grid points to define a plane called spline plane. And all the aerodynamic grids should be within the domain of the structural grid to avoid extrapolation, because the IPS method because the infinite plane, the boundary condition of the infinite plane is at infinity, that the deformation becomes 0. So this deformed infinite plane within the structural grid domain will follow the deformation of the structural grid, but beyond the domain of the structural grid, the deformation is uncontrollable. And also, if two structural grid points, they share the same location on the projected spline plane, the spline matrix will be singular. In fact, in all the spline method, you just cannot have 2 structural grid points that are too close. Okay. So the car name is called Spline 1 for infinite place spline. The EID is ID, and it's not used for it's not referred to by any other spline car, and the EID is used only for error message output. And the CP it refers to the ID of a Courtois car, and the XY plane of the Courtois car defines the spline plane. Then all structural grid points listed by the set G entry are projected onto the spline plane for performing the infinite spline method. And however, if the set K refers to a panelist 1, panelist 2, and panelist 3, in those cars, you list out the ID of the aerodynamic panels for spline. And however, if the program find out those aerodynamic panels belong to a ZAERO7 Bogota car, and then you don't have to specify this CP, because it will use the plane of the ZAERO7 as the spline plane as a default. And set G refer to a set 1 car. In this set 1 car, you list out all the structural grid point ID, and DZ is a linear attachment flexibility. So usually you use DZ equals 0, and so if DZ is not 0, then the infinite place spline will use a least square method to fit the plate into the deformed structural grid point. And so it's highly recommended that you always use DZ equals 0. EPS is a small number. The default is 0.01, and then EPS times IFC defines a small tolerance. IFC is the reference core defined in the LZ board.com, and so the program will use this small tolerance to detect that if any two or more structural grid points are located locations project on the spline plane are within this tolerance, is fatal error. The thin plate spline generalized the infinite plate spline method by incorporating some 3D aspect into the analytical solution of the IPS method. The TPS method maps the deformation at a set of scattered structural grid points in the 3D domain to a set of aerodynamic grids. So the TPS method is the best spline method when splining a set of structural grid points located on the fuselage surface and the corresponding aerodynamic body components. Because the TPS required the definition of a 3D space, so the TPS requires at least 4 non-coplanar structural grids. And if all structural grid points are coplanar, it's a fatal error. And similar to IPS, if 2 structural grid points are at the same location, the spline matrix becomes singular, and it's a fatal error. So the car is called spline 3, and this is ID, and all structural grid points are located in the 3D space. Therefore, the TPS method can be considered as a 3D spline method. And so it has ID. The EID is used only for error message output. It also refer to panelist 1, panelist 2, panelist 3, and set G refers to a set 1 car to list out the structure grid point ID, and EPS is a small tolerance, just like the spline 1 car. The beam spline is that if the structure model is a beam, and so you want to use a beam spline to spline this structural deformation to the aerodynamic panels, like on the 07 or on the body 7. So all structural grid, you have to define first. You have to define a spline axis. Okay, and then the program will fit. We use the infinite long beam to fit into this spline axis. And once it has this spline axis, it will project all the structural grid points onto the beam. Because all the structural grid points may not exactly along the same line, therefore it needs to project the structural grid point to this beam. And then you use an analytical solution of the infinite long beam and to fit the deformation at the structural grid point. Once it has the deformation of the beam, and then the program will connect the aerodynamic grid point to the beam and using a rigid bar. And so when the beam deforms and through this rigid bar, you can compute the corresponding deformation at the aerodynamic grid point. And so because unlike spline 1 and spline 3, the TPS IPS method, those methods only need the translational degrees of freedom from the structure model, but the beam spline also requires the rotational degrees of freedom. So if you have a structure model which is modeled by the beam, then you have to make sure all the grid point has 6 degrees of freedom deformation. And this is required by the beam spline. Also, if two structure grid points are located at the same location on the project line, the spline matrix will be singular. So the car is called spline 2. Again, and you have EID. And so unlike spline 1 and spline 3, the beam spline method requires both the translational degree of freedom and the rotational degree of freedom for both accurate displacement and slope spline at the aerodynamic boxes. so you give EID, and also you use set K to refer to panels 1, panels 2, panels 3, and set G refers to set 1 to list out the structure grid point, and DZ is the just like the spline 1 car is a flexibility factor, so you should always use 0, and EPS is the small tolerance, and CID, it refers to a quadrat car, and this y-axis of the quadrat car defines the spline axis. Okay, so once you define the spline axis, and the beam spline method will project all the structure grid points on this spline axis, and this quadrat car, the structure grid point location are those in the structure finite element model. So when you define this axis, and this quadrat car is located in the structure coordinate, not in the aerodynamic coordinate. So it's before the ACSID and the flip entries of the aero-z car are applied. Same as the even plate spline method. When you define a quadrat car whose XY plane is a spline plane, and this quadrat car also is in the structure coordinate, is not in the aerodynamic coordinate. So the last entry is called curve, and it can include the curvature effect of the torsion stiffness. The default is 1, and since MSC Nastran does not include the curvature effect of the torsion stiffness of the beam, specified curve equal to 0 gives the exact result with the spline 2 car of MSC Nastran. But the one thing we have to be careful that when we talk about if you use beam spline, if you use the spline 1 and spline 3 to do the force transferal, the conservation of forces are guaranteed. But this is not the case for beam spline. If you use beam spline for force transferal, and the conservation of the force is not guaranteed. And rigid body attachment is used in the case if, for example, if you have underwing store, and in the structural model, because the store is so rigid, so they only model the store mass. So they lump the whole store mass on a single grid point. And if this is the case, but aerodynamically, you have to model the store by body 7. Then you can use this rigid body attachment method to attach all the structural panels to this single structural grid point. And so, yes, the car name is called attach, and you have EID. And so for aerodynamic component not represented in the structural model, attach is used to transfer the displacement and the loads between the structural grid point and the aerodynamic component. So I just give you an example. So you have an underwing store, that is modeled structurally by a concentrate mass at a single structure grid point. And so set K again we refer to panels 1, panels 2, and panels 3 to list out the aerodynamic panel ID. And this entry refers to the structural grid point, a single grid point. And so you attach all the aerodynamic panels to this single structural grid point. And so internally, the attach method will connect all the aerodynamic panels to this structural grid point by a region bar. So when this grid point moves and rotates, the whole aerodynamic model will move accordingly. Okay, and sometimes if the if in the mode shape you short of some degrees of freedom, a typical example is the if the mode shape is measured by the ground vibration test, and because the ground vibration test, for example, if you have a missile body, then you put a accelerometer on the body to measure the translational degrees of freedom. Then, if we want to use the beam spline to spline the GVT measured mode to the aerodynamic model, but the beam spline require the rotational degree of freedom, degrees of freedom. But in the GVT, it's very difficult to measure the rotational degree of freedom. So if you can use this spline d.o.f to create the rotational degree of freedom at those grid point. For example, if I have two grid point and both has a translational degree of freedom along the z direction, if I want to create a rotational degree of freedom at this grid point about the y-axis, okay, and then you specify the dependent structure grid point, and you put ID here, which is 1, and in this case, then you say, okay, I want to create a rotational degree of freedom about the y-axis, so the degree of freedom is 5. Then you refer to this one, refer to the ID of the first point is called independent structural grid point. Then the degree of freedom at this grid point is 3, so it's a T3. Then I use refer to another grid point, which is ID is 2. So I refer the ID 2. Then this the translational degree of freedom at this grid point is along T3, so it's 3. Then if I want to compute the slope of this at this grid point, so the R2 of the grid point 1 equal to the T3 of point 1 minus T3 of grid point 2 divided by the length, the distance of this two grid, which is 10. Therefore, A1 should be 0.1 and A2 should be negative 0.1. In this case, I can create a degrees of freedom at this create a rotational degree of freedom at this grid point. So this card is called spline d.o.f. And sometimes when you do the spline, you for the force spline, and sometimes you want to use different spline strategy, and meaning you want to use a different structural grid point to create the force spline. And I will give you an example later. If you don't specify the spline F, then the default spline matrix for the force spline is the same as the displacement spline matrix. So you use ID spline. You refer to a spline 1, spline 2, spline 3 car, and in this spline car, and the set 1, the structure grid points ID can be changed. So you want to use different structural grids for to create the fourth spline. And you can display the spline mode shape on the aerodynamic model, and you specify an ID. And this plot mode car is not referred to by any other car. And this thing, because structurally, if you have a half-span model, you can import the symmetric mode and anti-symmetric mode using two assigned FEM executive control command. So when you plot the mode, you want to plot the symmetric mode or anti-symmetric mode. But if you have a full span model, you have to say async. The modes you want is an index of the structural mode. So if you put 3, then you want to plot the third mode. And the maximum displacement, because the structural mode is an eigenvector obtained by the structural analysis, the magnitude of the mode may not be of the same order as the size of the aerodynamic model. So you want to use this this, and this fraction will multiply by the REFC entry in the LZ car to define a factor, and then this one will be used as a factor to multiply to all the mode shape. So because sometimes the mode shape may be very small or maybe very large, because it's an eigenvector, and then you use this entry to control the maximum displacement of the spline mode on the aerodynamic model. And form, you can specify tech plot, pattern, ideas, fee map, answers, neststring, and nestl. And so you depends on what kind of which commercial graphic software you have, then you use the form to define that. And file nm is the name of the file to store the graphic data. And then if the file name is too long, and because we only give you 16 columns to specify the file name, if it's too long, then you can use the $sign and followed by an integer, and this integer refers to the ID of the exe file car. In this car, you can list 72 characters to define the name of the file, and this is the typical example of the plot mode car. And the spline modeling guideline, and most errors in error elastic analysis are due to the incorrect spline input. So you always want to use plot mode to check the spline input. And also the spline is performed on a component by component basis. So you have to select aerodynamic component. For example, you have a whole aircraft structure, you have a fuselage, you have a wing, you have underwing store, and then in fuselage you may use the spline 3, the 3D spline. The wing, probably you want to use spline 1 for the plate spline, and the underwing store, and you probably use attach. Okay, when you select the structural grid point, it's highly recommended to select structural grids that are supported by a strong substructure. So underneath, for example, you have to select the wing grid on the skin, and underneath is supported by either spar or rib. All the grid point on the fuselage underneath is supported by the bulkhead. So you never want to select a grid point which underneath there's no support substructures. And also because of the boundary condition of the infinite plane and being its displacement is 0 at infinity, extrapolation can lead to large error. Therefore, the aerodynamic box should be within the domain of the structural grid point. And so give you one example. If the aerodynamic component is modeled by ZAERO 7, and and structural model is modeled by the play, and you use the play spline, so spline 1. And if the structural model is a beam, and you use spline 2. If the structural model is a scattered grid point in the 3D space, then you use spline 3. If the structural model in the component is modeled by a single grid point, and you use attach. And in our spline method, you cannot have two grid points that they are too close. And if they are too close, that will lead to a yield condition spline matrix. And so the tolerance is set by the EPS parameter of the spline car, and this condition is reported as an error message due to during ZAERO execution, but certain scenarios exist where it is not detected. For example, if you have a structural wing which has an upper skin grid and lower surface grid, then aerodynamically you model this wing by C07. Then if you include all the grids from the upper surface and the lower surface wing skin into the spline 1 method, and the infinite play spline will project the upper grid and lower grid onto this spline plane. And then those two grids on the spline plane, they share the same location. So this will lead to a fatal error. So in this case, you can either select the grid from the upper surface, or also select the grid from the lower surface, but not both. And you may ask, okay, if I have modes which the upper skin go up and lower skin grid go down, and then in this case, if I only select the upper skin grid point in the play spline, and then I cannot capture this mode. And this kind of mode is called breathing mode, and it's a very high order mode. So those high order mode will have a little contribution to the error elastic solution. So once you have a error message from ZAERO tells you have two structural grid points, they are located within this tolerance, and but then if you look at your structural model, those two grid points in the structural model, they are not at the same location. But remember, the play spline will project the grid onto the spline plane, and on the spline plane, those two grids they share the same location. And also, if the structure model has a discontinuity, for example, if you have a control surface and you have to spline that differently, because the discontinuous structure, if you want to fit even play into this all the grid point here, and then the play will fit into grid point 6 and grid point 7. It will create a large error. So to circumvent this problem, you have to spline the control surface by one spline 1 car, and the rest of the panel by another spline 1 car. So in this case, I have used one spline car which refer to the aerodynamic panel ID 9 and 12, and the structure grid I include 5, 7, and 9, 10. Then when I spline the rest of the panel, I include grid point 1, 2, 3, 4, 5, 6, 8, and 9. Okay, and all in the spline method, all the aerodynamic panel must be splined once and only once. So all the panel ID cannot appear more than once in all the spline cars. However, the structural grid point can be appear in different spline cars. So I have one spline car, and which refer to for the control surface, and I have a grid point 5 and 9, and this 5 and 9 also appear when I spline the other wing panels, and so I refer to 1, 2, 3, 4, 5, 6, and 8, 9. So 5 and 9 appear twice in two spline one cont. Okay, if the structure model is a continuous structure, because modeling non-trapezoidal wing component require more than one ZAERO7, so I have to use two ZAERO7 cards to model this wing. But structurally, this wing is a continuous structure. Okay, so if you want to spline the mode shape from this structural model to this ZAERO7, if you only include grid point 1 to 8, and then if you when you spline this ZAERO7, you only include grid point 5 to 12, then you create two different spline different plate. Okay, so one plate fits into those grid, another plate fits into this grid. Then you may have a discontinuity in slope at this junction. So the correct method to do the displacement spline is that when you spline this ZAERO7, you include grid point 1 to 12. When you spline this ZAERO7, you also include 1 to 12. So those two spline cards actually they share the same infinite plate. Okay, so the displacement along here between those two ZAERO7, they are continuous. However, such a spline strategy for force spline may not be correct, because if you to create a force spline matrix, if this ZAERO7 refers to grid point 1 to 12, and this ZAERO7 also refers to 1 to 12, that means I want to transfer the aerodynamic forces from the aerodynamic model to those grid point. So that means if I have an aerodynamic box here which create an aerodynamic force, this force will have effect on the transferred grid point at the structure grid point. So this doesn't make sense. So in this case, then you want if you want to create a force spline matrix, you want to use the spline F card. So you create a different force spline matrix. So this ZAERO7 only refers to grid point 1 to 8, and this ZAERO7 only refers to the grid point 5 to 12. So you have to use different spline strategy for force spline, and you using the spline F Bogota card. And also, we need accurate rotational degree of freedom for the beam spline. So unlike the IPS and TBS method that only adopt translational degree of freedom at the finite element grid point, the beam spline 2 require both translational and rotational degree of freedom. So often in the structural finite element model, the translational degree of freedom are included as the at A set, okay, degree of freedom, where the rotational degree of freedom may be left out. Okay, if you don't include the A set, the rotational degree of freedom in the A set, then you use this mode shape solution to do the beam spline. It will lead to incorrect beam spline result. And in the case of using the GVT measure mode, and that normally involve only translational degree of freedom, then if you want use the beam spline to the missile and store body, may lead to incorrect spline result, because the GVT measure mode sometimes may not have the rotational degree of freedom. And so the solution is you use spline d.o.f to create the rotational degree of freedom from the translational degree of freedom. Also, you want to avoid extrapolation, and And so such a finite model can end up smaller than the aerodynamic model, such as when modeling a wing box to represent the wing structure. And so structurally, you only model the wing box, because wing box is the major load carrying component, and you don't model the leading edge flap and the trailing edge flap. You only model the mass of those control surface in the structure model. So in this case, the structure grid point, the structure domain is smaller than the aerodynamic domain. So if you use the place spline, you will do extrapolation. Okay, to avoid this, in the structural model, you have to create additional structural grid point along the leading edge and along the trailing edge. Then you connect this additional grid to the wing box model using either rigid element or RBE3 cont. And because you don't put a mass on those additional grid, so you don't change the structure stiffness and or mass. So the natural frequency should be the same. Then when you do spline, you can include those additional grid in the spline. In so doing, you can avoid extrapolation. And finally, you because the transpose spline matrix can transfer the force at the aerodynamic grid point to the structure grid point, based on the principle of virtual work, the conservation of the total force is guaranteed, but it does not guarantee the conservation of moment. So to ensure the accurate force spline, it is recommended that the structure grid point selected for spline be coarser than the aerodynamic grid point. Let me give you one example. So if I have if I have a two structure grid point located within one aerodynamic panel, because one aerodynamic panel creates an aerodynamic force called F sub A, and I want to split this aerodynamic force to the force at those two structure grid points, then I have an infinite number of solution. So maybe the force at this grid point going down, and this for the force at this grid point going up. So if you add F1 and F2, and it's guaranteed to be the FA, because the conservation of force is guaranteed, but the moment is not guaranteed. So in general, you always want to select less structural grid point than the number of aerodynamic panels. So the selection of the structural grid at the structural hard point, and so the point supported by the spot rib and bulkhead is recommended. And the SPLINEF bulkhead car allows the selection of the structural grid point to be different between the force spline and the displacement spline.